So welcome back. So this is the second part for today, and we're going to go on to Gauss's law. So a little bit about what we're talking about. We're literally talking about arrows or field lines, which are abstractions. They're literally made up. So we're going to do math on a model, and that might seem really kind of weird. We're going to draw these diagrams like we did in lab really carefully, and then we're going to do math on how well we drew those diagrams. I mean, in principle, that's exactly what we're doing. So this was all developed by Gauss, who was an amazing mathematician, who did a whole bunch of other things other than this, but this is named after him. So what we're going to talk about is a thing called electric flux. And electric flux is, sorry about that, let me get the pen back. So flux is basically the number of arrows. That's what you can think of it as. How many arrows are going through this particular window? So we're going to talk about electric flux in a uniform field. We'll start with uniform fields because they're easier, because all the arrows are parallel to each other. And then we're going to talk about electric flux in a non-uniform field. That gets a little bit more interesting. And then we're going to evaluate flux through closed surface. It turns out that if I look at the number of arrows entering or leaving a closed surface, it tells me about the amount of charge and the type of charge that's inside that closed surface. So that's like really valuable. And we're going to then determine good old Gauss's law to determine electric field at a given point. So electric field due to a point charge, electric field due to its symmetrical charge distributions, a spherical shell, cylindrical symmetry charge distribution like a wire, and a plane charge distribution. Okay, so that's where we're going. So we really want Gauss's law because it enables us to find the electric field at a given point near a family of charges much more efficiently than we could do using Coulomb's law. You know, we could have had sort of a sphere of charge, and we could say, okay, there's a little square. Let's take all these little squares and and we could do that math. We just did it. We just did it for a rod, but if we try to do it for a sphere, the math gets hard. So Gauss's law is a clever way of making that hard math into something that's really easy. And physicists will always look for the easiest route. So let's begin. So we're imagining a uniform field. I know it's uniform because all the arrows are parallel to each other. So let's remind ourselves. Uniform field occurs between the plates of a parallel plate capacitor, and you get a nice uniform field. In my mind, I envisage a path on top of an embankment and the path at the bottom of an embankment, and it's a nice uniform embankment. So this is, it's like that, There's the cross section. That's a nice uniform field. And you know that if you roll a ball down here, it doesn't matter where you begin, it's going to have the same kind of rolling properties, and it's going to be uniformly affected anywhere on that embankment, nice and uniform. Compare that with 2 point charges. So we have a point charge here and a point charge there. Let's call that one positive and that one negative. I really should have drawn it to the side so you can actually see the diagram a bit better. So let's change my orientation a little bit. So now I have a positive charge and a negative charge and a negative charge. And I know from lab that the electric field goes like that, etc. You've seen that, yeah? So, and I can imagine that as being like this, where we have a mountain, and it kind of goes into a sinkhole, and we have all these guys, contour lines going round. And now, where I got to change my color of pen, let's change the color of pen. Yeah, let's change my color of pen just so it stands out a bit. So now if I go to there. So now what happens is if I look at the slope of this. If I start rolling the boulder there, it's got a different experience than if I rolled the boulder there. You know, so the effect is not the same. The field is not uniform anymore. So it's more complicated. It's not impossible, but it's more complicated. So I divide the world up into those two, and I try to make sure that when I'm dealing with a uniform field, I know I'm dealing with a uniform field, because I can use certain mathematical simplifications. And if I'm dealing with a point charge field, I know I'm dealing with a point charge field, and I use the appropriate equations. And again, we'll be careful about what symmetries we use. So this is a uniform field because all the arrows are parallel to each other. Imagine the surface that is perpendicular to this field. So I take a piece of card and I say, oh, look, how many arrows come through that piece of card? It's like a, why? I'm going to say, because eventually it will be useful. You know, I'm going to say, just bear with me in mind. I'm going to call that the amount of arrows is the flux. So the electric field arrow density, how many arrows per square meter, is proportional to the magnitude of the electric field. That's what we found. When your arrows are close together, you have a stronger electric field than when your arrows are far apart. So let's literally say that's true. So, okay, my electric field arrow density is proportional to the magnitude of the field. The product of the magnitude of the electric field, that's my E, and my surface area A, will give me the number of arrows. If I have 5 arrows per square meter and I have 2 square meters for my card, it will be 10 arrows pass through it. If I have 9 arrows per square meter and I have 3 square meters of card, I'll get 27 arrows passing through it. So I can get the number of arrows by simply saying, take your electric field, the number of, and multiply it by the area. And it's as simple as that. We have a Greek letter here. This is phi, most people will call it. Sometimes it's called phi. Either one's acceptable, but if you say phi, sometimes people will scowl like I tend to, because I've always heard it's phi. But it can be phi. It's just 2 ways of saying the same thing. And it's great. So phi or phi is the number of arrows you have going through this imaginary surface. Okay. Let's make it a bit more general. Supposing, oh, I'm sorry, I got some, I used these notes before and didn't clean them, so let me clean up a bit. And I can't. Oh, this is going to be a bit rich. I'm sorry. I have 2 physics classes and they got here first, and I must have said save and as I left, and now it's in memory. So, okay. We'll live with it for today, and I'll just make sure in future that I have 2 versions of it. So now we say, well, look, hold on. Supposing that my electric field lines are not perpendicular to this area card. So supposing my area card is at some angle to the electric field lines, what am I going to do? And the answer is, well, you try and figure out what the perpendicular area is, because you want to multiply this electric field by this perpendicular area. And you go, how on earth can I do that? And you remember your components. And you add a right triangle. And if this was the angle, if this is the angle that you have, then you say, well, okay, there's my hypotenuse, and here's my adjacent. So adjacent over hypotenuse is equal to the cosine of the angle. So the adjacent area over the hypotenuse area is equal to the cosine of the angle. Works for lengths, works for areas. So then, okay. So then I can say, well, this little area, this E, this A dash would be A cosine theta. And so I can figure it out. Oh, so really more generally we say that my electric flux is equal to the electric field times the area times the cosine of the angle between, well, now it gets a bit messy. The cosine between the area that I've been given and the perpendicular to the electric field. That gets a bit long-winded. But it's true. It's not between the angle between the electric field direction and the area direction. It's not that angle. It's this angle here. And then somebody comes along and they say, I've got a smart idea. Why don't we just invent a area vector? Why don't we just invent this area vector and say this area vector will have a magnitude equal to the area of our card, and we'll have our direction which is perpendicular to the card's direction. And then you find, oh, now that works great. So we say our flux is equal to the electric field vector dotted. Always make your dots really clearly not that, but clearly that, so there's no confusion. Dotted with the area vector, and the area vector is defined as being this imaginary vector which is perpendicular to the area of interest and as an area, as a size that is equal to the area. And I know from math that this equals the magnitude of E times the magnitude of A times the cosine of the angle between those two vectors. You had a comment or a question?
I was going to ask, the angle that the electric field comes through this Gaussian surface is equal to the same angle.
So
Same theta.
it's this theta we want, and if my electric field is going through there, that's not the same angle.
It's not going to be.
It's not going to be the same angle, no. This is a big angle, and that's going to be a small angle.
Oh, no, it'll be theta. It'll be theta. It'll be 90 minus theta.
So you want that angle there between your A vector and your E vector is the same as this angle there.
Right, yeah.
This is the thing to remember, because very soon we give up on trying to visualize like this, and we say, just give me the area vector and I'm fine. So as a visual thinker, I go, oh, but I like having the diagram and all that, but frankly, it just makes life a lot harder when you might as well just get the area vector and you're away. So so this is it. Yes.
So the area vector is equal to a cosine alpha?
The area vector is A cosine, this is theta, A cosine theta, yeah. Yeah. I'm sorry, no. The area vector is magnitude of A, and it points in this direction, and you can represent it by an ijk. Okay? It's not that A cosine theta replaces that A. It's that the E is the magnitude of E and the A is the magnitude of A, and that dot product is given by that. So the cosine theta is there because it's a dot product. It's not there because it's a vector. Okay. I'm sorry. I'll just talk us through it. I'm sorry. I just didn't envisage this at all. So, and I can't do anything about it in class. It's not worth stopping and redoing it, because by the time I get it, yeah, it's not worth redoing in class. So just bear with me. I'm so sorry. So this says the electric field of a 2 Newton per Coulomb point in the positive x direction. So you draw your 2 Newtons per Coulomb electric field. It's in the x direction, so you draw it in the x direction. And then you say, what is the electric flux that passes through a 3 square meter, so there's my 3 square meter area, which is in the YZ plane. So I'm visualizing here. And what I've got here is I've got 3 ways of doing this problem. So the first is I recognize, oh, these are perpendicular to each other. That's how we began. So I say, well, my flux is equal to just my electric field magnitude multiplied my area magnitude, because they are 90 degrees to each other. They're perpendicular. So my flux is equal to 2 times 3, which equals 6. So that's not bad. Newtons per Coulomb. There's my field times meters squared. There's my area. So that's okay. That's the simplest one, but that relies on the fact that they are perpendicular and you recognize them to be perpendicular. Well, I'd rather not learn a special case for that, so let's try and do it a bit more generally. And what I can say is, well, okay, my flux is equal to the magnitude of my electric field times the magnitude of the area times the cosine of the angle between the electric field and the area vector. So I can look and say, well, my electric field magnitude is 2 and my area is 3. And when I look at this diagram, then these guys are parallel to each other, and so I have the cosine of 0, and of course the cosine of 0 is 1, and so that goes to 1. So I have the same answer, but just I got it by moving from a different starting point. And sometimes that's a useful way to go. And in a way, the most generic way to go is I say this electric field has an area as a vector which is, well, what is it? It's 2 newtons per coulomb in the x direction. So let's call this 2I plus 0j plus 0k. There's no components in the y and the z direction. Agreed? Everybody sees where this comes from? Because that's a conceptual step there. You look at your diagram and you go, oh, it's only got x components, so it's going to be 2I. And then you say, well, what's my area vector? Well, my area vector is going to be 3 units long, and it's going to be perpendicular to the y and the z plane. Oh, that's going to be 3I plus 0j plus 0k. So I've broken my electric field and my area into ijk. And then I simply do the dot product. And I go, well, it's going to be the dot product between 2I plus 0j plus 0k, dotted with 3I plus 0j plus 0k. And I go, well, always multiply the coefficients together. So 2 times 3 is 6, and then 0 times 0 plus 0 times 0, which again gives me the same answer. So I have these 3 different ways of approaching this answer, this question, and all of them work. Because this is the simplest type of problem I can ask you. If these are not perpendicular, the first method is no good. And if you don't know the angle between those 2 vectors, then the second method is no good. I suppose you could say if you don't know the ijk for those vectors, then the third method is no good. So you tend to play off between these 2 vectors, where you know the angle and you know the magnitudes, or you know the ijk's. But I'm a teacher, and so I like to give you things that are a bit more interesting. So I'll tell you now, as often as not, I will give you the ijk for one of them, say the E, and I will give you a magnitude and a direction for the other one, say 3 meters squared in the positive y-axis. So then you have to decide. No, you can't, because this might be 4I plus 7j plus 9k. I drew it as 60 degrees because I want to visualize it, but I have no idea where this arrow is. So this is going to be newtons per coulomb. So you've got a fundamental choice to make. Do you try to find the magnitude of this ijk and also this angle? Good luck with that. Or do you try and find the ijk for this one and use the dot product? And that's the good money is on, because I'm not going to give you some wacky angle. I mean, I'm going to give you something that's identifiable, because we've only got so many minutes in a test. But that's the philosophical choice you've got to make. Of, do I go with the angle and the magnitude, or do I go with the ijk? Yes.
I didn't quite catch why the area vector is just 3I.
Because it's defined as having the magnitude of the area, and I told you it was 3 meters. And I told you it was in the YZ plane. So if it's in the YZ plane and the area vector by definition is at 90 degrees to that area vector, that means it must be in the x direction. Yeah. So good question. Good question. Okay? So that's the kind of game we're going to play. Oh! Do this one for me. Okay? So it says an electric field, 7 newtons per coulomb, is in the positive x direction. What is the electric flux through a surface that is 2 square meters? If the normal to the surface, I better draw a diagram for this because it's probably a bad explanation on my part. So the electric field is there, E, And this is the normal is 70 degrees elevation above the positive x-axis. Remember that from projectiles, angle of elevation above the positive x-axis? So let's call it a day there. Let's stop it and let's see what people have said. So most people saying B, a C. There's a C and a couple of E's there. That's fine. So let's do it. So let's have a look. Strategies. I know that's at 90 degrees. Oh, while I turned the video off, I put this little thing just to exemplify where the area is. I didn't give you the area. I gave you the normal to the area because it says 2 meters if the normal to the surface is inclined at 70 degrees. So then I go, oh, well, that's a bit of a clue. Flux is equal to, it's going to be E, the magnitude of E, times the magnitude of A, times the cosine of the angle between them, as long as this is the field vector and this is the area vector, because it also equals, let's put the whole thing down, E dot A. I think of E dot A as been the main equation, and this is something I get from there. So then I say, well, okay, my flux is equal to, what was the magnitude of E? My magnitude of E was 7 newtons per coulomb. That's 7. And my magnitude of A was 2 square meters. That's 2. And then it's going to be cosine the angle between, which is cosine of 70 degrees. So what does that work out to be? 14 cosine 70. So what is that? 4.8. Whoops-a-daisy. 4.8 newtons per coulomb meter squared. I learn it as E times A. So newtons per coulomb times meter squared. So that's kind of nice. Not bad. Yeah. Do that one for me, please. An electric field with that IJK passes through an area denoted by, that means, you know, represented by 3I plus 4J minus, I'm sorry, there's a negative in there, minus 2K. The word processor split up that equation, split up that IJK, meter squared. Then what is the electric flux through the surface? So you can visualize. There's my area vector. There's my field vector. My field vector was 4I plus 2J plus 3K. Newtons per coulomb. And my area vector is 3I plus 4J minus 2K meters squared. So write down your equation and then decide what you're going to do. So let's have a look. Let's stop there. And what do we get? Many people saying B. Let's see if we agree. So we have our flux. Our flux is equal to E dotted with A, and they are both vectors, so put the little arrows on top, which equals the magnitude of E times the magnitude of A times the cosine of the angle between. And I'm going to go with 2 IJK vectors. So I'm going to say my flux is equal to, my E vector is 4I plus 2J plus 3K. And then I'm going to dot that with my area vector, which is 3I plus 4J minus 2K. And then I'm going to do my dot product, where you just multiply the powers, the coefficients together. So that's 4 times 3 plus 2 times 4 plus 3 times minus 2. I just took the first one times the first one, added to the second one times the second one, and the third one times the third one. Remembering that the negative sign must be included. So my flux is equal to 12 plus 8 plus minus 6, which equals, that looks like 14 to me, 14 newtons per coulomb times meter squared. So that'll be 14. So B is the true answer. And this is, I got to tell you that we did this in Physics 1, and it's coming back in Physics 2, and it's a shame when people don't get this right because they just don't remember how to do a dot product. So dot products and cross products are going to keep coming up from now on. It's just, they're going to keep coming up. So just don't give points away from a mathematical, handle turning issue. If you don't get it, give points away because you don't conceptually understand what's going on, not because of that. So, okay, so the next little bit we're going to do is we're going to start heading towards this idea about a closed Gaussian surface. And in principle, this does not rely upon symmetry. So I have a potato shape. And I imagine that I have a whole bunch of, I'm going to take there's one electric field line coming out of the potato shape. So I say, oh, that's like a little card. So what did I do? I took my electric field line, and I took my area vector line and the angle between, and I did math on that. So I could do that on a whole bunch of interlocking little cards that do this entire, surface, just like putting jewels onto a baseball or something. I can fill this full of these little cards, and I can do the grand sum of the flux, which is, what does flux mean? Number of electric field arrows, basically, how many electric field arrows you have. So I can sum all the electric field arrows that I have escaping this thing. Well, doesn't the number of field arrows depend upon me? Well, in the past we said draw as many as you like, and now we're going to say we're going to have a certain number you draw for a certain amount of charge. We're going to quantify things, so we're going to get to that. But that's my visualization. I have a potato. Inside it, by the looks of things, inside it there's a charge. I've got one field line that I'm interested in coming out. But, frankly, there'd be a whole bunch of field lines coming out of this, and I could do this problem, over a whole bunch of things. So I say in a non-uniform electric field, our equation works for small elements, just little pieces of card. We define the little area vector A, whose magnitude represents the area of the ith. That means just 1 out of I element surfaces. The direction of dA, the little area vector, is always perpendicular to the surface element. So we say our little bit of electric field, our little bit of flux is equal to, well, it's our little bit of electric field and our little bit of area vector dotted together, which is the magnitude of that electric field times the magnitude of the area times the cosine of the angle between. We can find the overall effect by summing the contribution. So we're going to do, we're going to do a summation. But in the limit, oh dear, in the limit it goes to the surface integral of E dotted with dA. And again, it kind of, on a potato shape like this, horrendous problem. So we're going to make progress by looking for, we're going to get good at looking for symmetries that help us mathematically. When you think about it, I'm imagining a closed sphere here. So imagine a closed sphere. Take a slice through the closed sphere so we can see what's going on. The electric field line is going like that, basically. So in this first example here, the electric field is going through, and my area vector always points perpendicular to the area. Well, there's my area vector. It could be that, or it could be that. They're both perpendicular to the area. But the rule is it always points to the outside of the enclosed volume. The area vector leaves the potato. It doesn't go into the potato. It leaves the potato. So rather than drawing my area vector inwards, it has to be drawn leaving the area. What do you notice about the angle between these two? Is it more than 90 degrees or equal to 90 degrees or less than 90 degrees? It's less. And what do you know about the cosine of a number of an angle between 0 and 90? What's its sign? Positive. So the fluxes when the electric field is leaving the area vector are always positives. And what can you tell me about when the electric field is coming in and the area vector is pointing in that direction? What's this angle? So that's going to be more than 90 degrees, but less than 180, which is always a negative. And so when the electric field is entering the potato, you have a negative flux. Positive when the electric field is leaving the potato, negative when it's entering the potato. And then the third thing is when it's grazing, when it's at 90 degrees, well, that's the cosine of 90, which is 0. So this is always going to be positive, that's always going to be negative, and that's always going to be 0. So 3 little rules. And then we say, okay. What I'm going to do is I'm gonna go here. And I'm going to do this for us because I want this to work out. So I have a positive charge. And I want to know the electric field at a point P. And I know that they are r meters away. Fellas, please. Fellas, please. I want to know that they're r meters away. So now here's the thing that people have a bit of trouble with. I'm going to decide where the Gaussian surface is. You are the people who decide. But I want some symmetries here. So I'm going to say, you know, I'd like the electric field on that Gaussian surface to be constant. Now, how does electric field fall off with distance? What kind of law is it? Inverse square. We know that because our electric field is equal to KEQ over R squared. It's inverse square. But it depends upon the distance squared. So I can get a constant E. Q's not going to change. So I can get a constant E by doing a nice spherical Gaussian surface. Turns out that although in principle, you know, there are an infinite number of possible Gaussian surfaces, there's certain patterns that just lend themselves mathematically. Spheres, cylinders, those are the 2 main Gaussian surfaces that you deal with. And then the second thing I would like is to have a area which I can calculate. And the nice thing is I can calculate the area of the surface of a sphere nicely because I know the equation for it. Okay. So what I'm going to say is I've got to be careful because I'm trying to derive the thing I'm more practiced in using. So what I'm going to say is that my electric field is equal to KEQ over R squared. And I'm going to imagine a little area here. So here's my E. And then my area vector dA is there. And I'm going to say, oh, my area is equal to the sum of my area is equal to 4 pi r squared, because it's a sphere. Yes? Okay. So now, the other thing I have to remember is that KE is equal to 1 over 4 pi epsilon naught. Epsilon naught. Epsilon is a constant, and pi is a constant, and 4 is a constant. Electrical engineers tend to use epsilon naught rather than Ke because it's more fundamental, but physicists tend to use Ke, Coulomb's constant. So I'm going to combine these guys together. I'm going to say, well, E is equal to KEQ over R squared. And if I multiply both sides by A, I'm going to multiply this by 4 pi R squared. So this is going to equal, I'm going to stop in like a second or two. So this is going to equal, the R squareds go away, and that's going to be 4 pi Q Ke, and this is going to be A dotted with E. And then I bring in my Ke is equal to 4 pi Q. And rather than Ke, I'm going to put 1 over 4 pi epsilon naught. And so the 4 pi's cancel. I don't believe I did this. So AE is equal to Q over epsilon naught. And that basically is the flux, which equals Coulomb's law and Gauss's law. So next time I'll put the notes up so you can see it, and we're going to use Gauss's law for the future stuff. But can you see how it's relatively simple? The number of flux lines equals the charge over a constant. That's as simple as it gets. Okay, I'll stop now.